Hi, my name is Dominic Kupal, a protocol expert at JDSU. Today I will teach you how to debug the 12G SAS transmitter training with the Xgig Analyzer product. You need to launch the Xgig Trace Control application to take a capture. You should use at least 300 megabytes of buffer to capture the entire training sequence. I will discuss a way to reduce the capture size at the end of this presentation. Once you got the capture, you open it with the Xgig Trace View application. My capture contains only a couple events in the main Trace View grid. I captured the end of the OOP sequence, followed by the transmitter training sequence, followed by two identify address frames at the end of the trace. The main grid shows only one training frame per port for the entire transmitter training sequence. That training frame corresponds to the transmitter training complete frame, the first frame seen with the train comp bit equal to 1. The inspector window at the bottom of the grid displays the details for the line selected in the top grid. Here are the details for a SAS training frame. The frame contains 32 bits of information, 16 bits of control, followed by 16 bits of status. You can right-click on any field in the inspector window to get a full description for the field. This is a very good way to learn about subtleties of the protocol. The description also contains a hyperlink to the protocol spec. You can click on it to bring up the protocol spec in the Internet Explorer. To view the entire training sequence, you need to look at the DWORD view. The top grid and the DWORD view are synchronized together when the double arrow toolbar button is pressed. You can click the training frames in the top grid and the DWORD view will automatically highlight them. Again, these are the training complete frames. So we will add a bookmark, port 5 training complete, and port 6 training complete for each of them. Overall, the training sequence purpose is to optimize the electrical signal coefficients for the transmitter, the cable, and the receiver all together. There are 3 electrical coefficients being tuned at the same time by the training frames, and they're called coefficient 1, 2, and 3. Each training frame has one control and one status field for each coefficient. The coefficient control field has 3 possible values: hold, decrement, and increment. The coefficient status field has 4 possible values: ready, is maximum, is minimum, and update complete. During the training sequence, each port will send repeatedly training frames followed by 58 DWORDs of scrambled training data. The receiver will descramble the training data and check if it matches the expected pattern. If it does not match, it means that the signal quality is poor and the receiver will request the transmitter through a training frame to increment or decrement one or many of the coefficients in an attempt at improving the signal quality. On the other side, when it receives such a request, it performs the coefficient increments or decrements, and then it sends the next training frame with coefficient status being set to one of 3 possible values: update complete, or is set to maximum, or is set to minimum. At this point, the other side knows that the coefficients have been updated, and it can check again if the scrambled training data matches the expected pattern. This process goes on and on until the signal quality is adequate, or until a timeout of 500 milliseconds. When the signal is adequate, the receiver will mark the training frames with the status training complete, as it is the case in our sample trace. The transmitter training is performed by both ports in both directions at the same time. You got to debug each port transmitter training independently. Okay, now we're done with the theory. Let's get back to our trace. In the DWORD view, we are only interested in the training sequence section. So we will filter on the event type equals SAS SATA training frame word by double-clicking inside the port column of the DWORD view. Then we set up the filters and click the filter button. From there, I'm interested in knowing how long is the training session. To do this, I will scroll all the way to the top of the DWORD view. Double-click in the timestamp column to bring up the delta time calculator. Then I will scroll all the way down to the last training frame. In the delta time calculator, I'll see that the training session lasted for 255 milliseconds, so under the ultimate timeout of 500 milliseconds. Now, going back to the top of the DWORD view and paging down through the training frames, we can see that there are a lot of them. But they're mostly the same. They all contain a value of hold on the 3 coefficient controls and a value of ready on the 3 coefficient status. These are uninteresting. We are interested in the coefficient increments or decrements and the status being different than ready. To isolate only the interesting training frames, we will perform a quick find again by double-clicking inside one of the training frames. Note that we already have a filter applied in the DWORD view. This is visible with the green toolbar button being pressed, and also because the Quick Filter List button is enabled. You can see the current filters being applied by clicking the Quick Filter List button. The new filter will be applied on the top of the previous filter. So here, we will set up the Quick Find criterions to check for each coefficient control being different than hold, and each coefficient status being different than ready. Also, we add one more criterion to check for the status equaling training complete. Once this is done, we hit the filter button. While the filter is being applied, you can see a white bar moving forward in the histogram, showing the filter progress. After a couple of seconds, you can see the result. We can see that the receiver on port 6 requests decrementing the coefficient 3 one time because it detected a poor signal. Then the other side performed the decrement and posted an update complete for coefficient 3. Again, the port 6 receiver evaluated the signal quality and it found it adequate this time. It posted the training complete status. At this point, port 6 is done with training. On port 5, the receiver does not request any coefficient update. so it finds the signal quality adequate already. It eventually posts the training complete status as well. So we are done debugging this transmitter training sample trace. The training session lasted 255 milliseconds, and there was only one coefficient decrease during the whole session for coefficient number 3. The TX training session succeeded. Before we end this presentation, I want to show you a way to reduce the buffer size required to capture the entire training sequence. Xgig Trace Control 6.1 has a capture option allowing to filter out any redundant training frame in the capture. In that case, when several training frames are equal in a row, it captures only the first one until a different frame is seen. This is enabled when you select the option Capture Only OOB and Speed Negotiation Events. This option reduces greatly the buffer size needed to capture a full transmitter training session. To summarize on transmitter training debugging, you can use any analyzer to view your traffic on the wire. But if you want to debug within a capture, you got to use the JDSU Xgig analyzer. There's really no way around it. Again, my name is Dominic Coupal from JDSU. Thanks for listening to my presentation.